The way to solve differential equations numerically is to discretize your problem. What you do then is to think the other way around and say that, okay, let's assume that I already know the solution in very many points, and take my differential equation and exchange all the derivatives with function values. So you exchange the first order derivative with an expression of function values to the left and to the right, and the same with second order derivatives. And what you get then is a massive matrix equation that you need to solve. And if you don't want to solve that by hand, it's time to introduce Comsol Multiphysics by solving a simple mass transfer task. In this problem we have a ventilation duct, and it looks like this: straight part and then a bend, and it's 0.4 meters wide here and 0.4 meters wide there, 0.8 meters in the straight part here, and then the bend has an inner radius of 0.4 meters and an outer radius of 0.8 meters. And we know that the air is standing still, so the fan has broken, and we have ethanol in air, and the diffusivity for ethanol in air is 1.35 10 to the power minus 5 square meter per second at the temperature. We don't know the temperature, but we have been given the diffusivity. And we know that at this inlet here, we have 1 mole per cubic meter of ethanol, and over here we have a concentration of 0. So let's shift to Comsol and click Model Wizard. And the first step is to choose model dimensions, and we don't care now how deep the ventilation duct goes into the plane, so we are going to solve this as a two-dimensional problem. And depending on what you installed in Comsol, you get different options. The ones I have installed in Comsol Multiphysics 5.3, the interesting thing here is chemical species transport and transport of diluted species. So we add that physics to our model, that set of differential equations, and when we have done that, we click Study. We don't want to add any other physics to our model. It's only one physics that we need, and the kind of problem we're looking at is a stationary problem. We're not looking at how it develops over time, so we click Stationary and click Done. And after a while, we're greeted with this window, which has a lot of information in it. You see you have a document here. It's currently called Untitled. And in that document, there is the possibility to make global definitions like materials. And in this document, we have our component that we're going to study. And that for that component, we have definitions, geometry, materials, and the physics. The transport of diluted species, we only have one physics because we only selected one physics. And then we have mesh, study, and results. And we go about in the same order here. We don't need to make any definitions in this simple problem. So we go to geometry and draw our domain. And you can do that either by selecting tools here or by left clicking on geometry. And let's choose rectangle and put in the numbers. It should be 0.8 meters wide and 0.4 meters high. And click Build Selected, and it's printed for you. The next step is to make the bend. So let's choose the tools over here. But we actually need to zoom out because we want to draw something at this end. So zoom out a bit. And with this tool here, you click 3 times where it should start, so there. And then let's see, 0.4, that's, if this is 0.8, this is 1.2, so that's 0.4, we click there, and then you click a 3rd time, that should be minus 0.4 on the y-axis. And let's try and left click somewhere, see what happens. So if we left click, we are done with that tool, and it connects the final dots, the final dot with the first dot, and you see that that wasn't nice, right? We want this part to the right to be part of our domain and not the part to the left. So let's delete this one, left click and choose delete. Left click or right click, I never remember which. I have my computer set in a certain way. So it might be right click on your computer. So let's do this again. 0.4 and then 0.4 down. And then we're done with that bend. And now we want to make a straight line here, but then we need to select another tool. So we select the straight line and go to 1.6 because that's 0.4 to the right. And then we reselect this bend again. And you go up and go over here and click again. And now we're done. So let's left or right click, whichever it is on your computer. And we're done. So before we tried the zoom out, let's try the zoom in. And now you see that I don't see my entire thing here. So let's click on zoom extents, because that's a more intelligent zoom in. It makes sure that your window is filled with whatever you have drawn. So next step is materials. So here you can select materials. In our case, we have air and ethanol. So how to do that? Well, we skip materials here actually because we have been given a specific diffusivity to use. So we skip that and go into our transport of diluted species, our physics. And there you see 3 different things by default. And this one is filled, transport properties, and this last one is filled, initial values. And this one in the middle is not filled. And this is because the first and the third here that is things that are valid for the entire domain, and this thing in the middle is something that's valid on the boundary. So let's select the first one, the transport properties. Here you could enter the temperature. We don't know the temperature and we don't care because we're going to fill in a diffusivity straight up just as a constant. But you could add a temperature here, and below here where it says diffusion coefficient, you could add an equation containing the temperature, but we simply put in 1.35 10 to the power minus 5. The way to write that in programming is to write e minus 5. So e minus 5 is times 10 to the power minus 5. What do you have more here? You can select coordinate systems. We just skip that. Velocity field, we said that the air is standing still, so there should be no velocity field. And yeah, let's comment this one as well. You can choose here different kinds of diffusion coefficients. Isotropic means that it's the same diffusion coefficient in all directions, and since we have air, that's reasonable, right? Okay, the next field one is initial values. And I should say that, yeah, the same thing as over here. Domain selection. Currently we have both domains selected here in the transport properties, and that's nice because we want to have this diffusion coefficient the same in both parts of our domain. And with initial values, well, we don't care because we are solving a stationary problem, so initial values don't matter. What about the boundary conditions? By default, it has taken everything as no flux, so there is no flux across any boundary here. Now we draw our geometry as 2 separate parts, and Comsol guesses that, yeah, these 2 parts fit together, right? So the boundary 4 here is not applicable, so that's not a true boundary. It's just something that was created by the way we draw our system. So we want to set a concentration over here as 1 and a concentration over here in the outlet as 0. So how do that? Well, you go here and you left or right click, whichever it is on your computer, and you get different options. Up here you have all the filled things, all the things that are valid for the entire domain, and here you have all possible kinds of boundary conditions. And depending on what version you have of Comsol Multiphysics, you might get slightly different options here. But the thing that we want to use is concentration. So we wanted to have this boundary here. So just click that, and then it appears there. And we only have one species, so let's select that species and write in 1 mole per cubic meter as the concentration at that boundary. We also want to have a concentration over here, but that has a different value, so we need to create a new boundary condition there. So select concentration again, and then click there, and it appears there. And select your species, and yeah, 0, the default value, is actually what we want. So we're done. And if you want to, you could of course say something else here. It has a default label, concentration 2. You can call it concentration out. You could even write in a symbol here and say, call it C out, for example, and then define that thing in your definitions instead. Okay, but let's go to mesh, because we're done with the physics. Let's just click build all and see what the default is. The default looks like this. So it divides, Comsol divides our problem into triangles, and it actually calculates only in these corners, and then it interpolates all over. And what happens if we take a finer mesh is that you get more triangles, more calculations, more computational time, and less, of course, than less computation time. But let's choose the normal to start with and see what happens. And time to compute. So you go into study and you click compute and wait a while. Okay, so that's our solution. How do we know that this is a good solution? Well, you could go back to mesh here and make something more detailed. So more calculations, click build all, go back to your study, and you can update the solution now. And it seems to look the same. So what that means is that if we increase the resolution, it didn't affect the solution. So our solution seems to be stable. It doesn't change when we increase the resolution. And you should, if you have, typically you computational power is a bottleneck, so you want to have as fine as a mesh as you need, but not finer, because a finer mesh will give you longer computational times. Okay, so this plot was given by default, and you can see here it's a surface plot, and it's a surface plot of the concentration. I want you to draw something slightly more interesting. Then you do like this, you click here, and depending on what version you have of Comsol Multiphysics, you get different options here. Component 1, and that's the same name here as we have over here, right? So we go in there, and in there we have definitions, geometry, and we have transport of diluted species, our physics. So here it can take things from the equations that we use, and the equations we use, that's defined when we select the physics, right? So currently we have C as in concentration, but I want you to draw it for total flux magnitude. So you select that, and then it changes here, an expression, and it changes the unit, of course. And then you click plot to update the plot to now show this value. And when you do that, try to figure out why it looks the way it does.